Well, good afternoon, everyone. Thank you. Thank you for sticking around till the second last session. The talk in the speaker room today was, all the cool kids have sessions on the last day. Maybe thank you for staying. Thank you for being interested in C++ AMP, accelerated massive parallelism. My blog and Twitter ID are both on the screen, if you don't already happen to know me. Usually when I introduce myself, I say, well, I've been using C++ since before Microsoft had a C++ compiler, which is a really long time, over 20 years. And every once in a while, stuff comes along that's really, really exciting, and this technology is one of those. It was announced about a year and a week, maybe a year and 2 weeks ago, and the minute it was announced, I was all over it. I wanted to know more, wanted to start being able to use it. Ended up talking to the team, ended up agreeing to write a book about it. One chapter away from at least the first draft of that book being complete, and that's going to be published by Microsoft Press if you are interested. And along the way, I've learned an awful lot about this technology, and it's very accessible, but it has a lot of depth if you want to go there. But let's sort of start with a context of why anybody would even want to use something like C++ AMP. I've stayed in C++ while other people have gone off to do other languages. I've done some other languages as well myself, but I keep coming back to C++ a lot. And many times it's for one reason and one reason only, performance, and especially control of performance. So if speed at runtime is what matters the most to you, chances are the language you're going to choose is going to be C++. Many of you are probably already familiar with some frameworks or libraries that you can use that make your code faster. Like, how many people here have ever used Boost? That's about half the room. Okay? Keep your hand up if the reason you used Boost was because it's so elegant and beautiful. Gee, I got one half a hand. Okay. But boy, oh boy, it could make your code fast, right? That's important to us. Closer to sort of Microsoft's heart would be the PPL, the Parallel Patterns Library, as a way to start using all of the cores on your machine, if you have a multi-core machine, which most people do these days, without changing your code very much, and probably without changing your logic at all, just replacing a sequential for loop with a parallel for loop. But of course, performance isn't everything. It's not the only thing we care about. We also care about our own productivity. And if you're a Windows developer, if you're a Visual Studio user, and I tell you that you can make your code a lot faster, but what you need to do is A, learn a new language, and B, start using a new tool, and C, accept the fact that it doesn't have certain features that Visual Studio has, then maybe you wouldn't be so motivated to go and take on that ability to get that performance. One of the things that's really important to C++ AMP is giving you a productivity that comes from using a language you know in a tool you know. And then there's the matter of portability. I meet a lot of C++ developers who write standard C++. They can compile it with any one of a number of different compilers and even run them on various platforms and hardware. Even if you know you're targeting Windows, you obviously want to be able to target all the versions of Windows just as equally as each other. You want to be able to deploy without necessarily having to write an installer in order to deploy your application. And you want to be able to run that application on anything that's running Windows as opposed to one specific set of hardware. So, for example, I doubt very much that any of you have said, I'd like to write an application for my business today, and I want it to only run on computers that have graphics cards from one particular vendor. I'm going to choose what graphics card it's going to run on. Anyone's writing that? No. Well, if you want to accelerate your code with the graphics card, that has been what you've had to do. You've had to pick which graphics card you'd like to accelerate your code with. So the story of C++ AMP is accelerating your code with anybody's graphics card, as long, I must say, as long as it does DirectX 11 or better, which is not a very high constraint to set. So I'm going to tell you a lot about what it is, but first I want to show you why you care. This is an MFC application written by my co-author on the book, Aid Miller, who's written some amazing samples and demos for the book. And what this does, and I should get it started sooner rather than later because it takes a little while on the CPU, is it turns a picture into something that's kind of like a cartoon. Okay, we have a timer running on it. It took about 4 seconds to do that. So it goes through the pixels and looks at the neighbor pixels, and if they're close to the same color, it makes them the same color. And it does that, and then it does that again, and then it does that again, and I can actually control how many times it goes around and does it. Obviously, if you want to do it 20 times, it's going to take a lot longer than if it does it 2 times. And then after it's done that, it draws these little black borders between areas of different colors. So that took 4 seconds on a single CPU. You would not have a drop-down like this in your real code. Obviously, you'd pick away, but we just have a series of different approaches to the exact same problem. So if I use the PPL, the Parallel Patterns Library, and now I have 4 cores in this machine, so if I reload the picture and then cartoonize it, now it only takes 2 seconds from 4.5 seconds. I have 4 cores in this machine. I can usually get it in about a third of the time. So it's taking a little longer today, but that's okay. I could even give it another shot and see if we get down under 2. It wants to stick at 2. All right, I'm not going to argue with it. Still, cut the execution time in half. Most people would be very happy if they could cut the execution times of their calculations in half. Now I'm going to let AMP have a go at it. Now watch quickly. It's done. 50 milliseconds. So single CPU was 4 seconds, and in North America it's 6 seconds, by the way. I think your power is overclocking my CPU. I think I should move here for performance reasons. But 50 milliseconds, like that's kind of a big deal, right? So you can go from 5 seconds to 50 milliseconds. That's 100 factor. And most people want to know how they can make their code do that. And that's why that's my first demo. Let's talk about how you can make your code do that. So AMP stands for Accelerated Massive Parallelism. And the accelerator that you're going to use is a GPU, a video card. If you, as I did, watched the sessions a year ago when it was first being announced and first being talked about, you will hear hints and dreams of eventually there being other accelerators. Today, you can basically treat the accelerator and GPU as interchangeable words. But they're working on being future-proof by having this more general concept of an accelerator, that which you ship your work to, it gets done, and then you get the answers back. Now, C++ AMP, very importantly, the C++ part of the name is absolutely fundamental to this whole thing. You are going to write code in C++, not in some C-like language. In C++. You're going to use Visual Studio, and then your code is going to speed up. The parallelizable parts of your code are going to speed up by 20 times, by 50 times, or you just saw it speeding up by 100 times. And that's not outrageous and not a carefully cherry-picked demo. There are other business problems that speed up like that too. It's basically a library. There is actually some tiny language changes, which I will talk to you about when we get there. But what really matters is that it's a library. And this library is part of VC Redist, which means whatever you're doing today to deploy a C++ application that you built with Visual Studio, that's exactly what you do to deploy an application built with C++ AMP. You don't need to write an installer or include any special things or impose any requirements on the target where you're going other than having a video card that goes up to DirectX 11. Now, people always ask me, what if you don't have one? And I do have an answer for that, but I'll talk about it a little later towards the end of the session. That portability of being a library and being included in VC Redist is even further made portable by the fact that they took the spec, the definition of what that library has, the API, and made that an open specification, and encouraging other compiler vendors, if they want to also implement a C++ AMP for their universe. So the Microsoft version builds on DirectX, comes with the Visual Studio. There could be C++ AMP implementations for other ways of living, if you like, which would give you the opportunity that you could take some code and move it around from place to place and have that code still get acceleration from the video card in exactly the same way. Intel has apparently already done this. I don't know who else has or is going to, but I can see a big benefit of that happening across a variety of compiler vendors. And of course, it's portable across hardware. I happen to have an AMD card in here, but I have run these XEs on a tremendous number of different cards, AMD cards, NVIDIA cards, not a problem. It's a consistent experience across different hardware. CPUs and GPUs are very, very different creatures. And it helps if you know a little bit about what makes them different. The CPU is general purpose in a way that a GPU could never hope to be. It's very good at doing whatever you want in any old order. It has a sort of branch prediction and deep caches, a lot of automatic goodness for you that it's fine with looping around, forking, rejoining, recursion, accessing all kinds of random seeming memory all over everywhere in any old order, and it'll make a pretty good job of it. What the GPU likes to do is access a lot of memory, especially a whole sort of consecutive clunk of memory, and then do the same very simple thing to every single element in that memory. If you think about writing a video game and what has to be done to calculate pixels, it's things like take all of these and subtract 1 from them. Take all of those and add 2 to them. GPUs love doing that sort of thing, especially if all of those is 1,000,000. They're really happy doing that. And really happy means higher performance for you. The other thing you need to know about the GPU is that it uses a lot less power. So in my demos, I'm going to be focusing on how long things take to run. But in many ways in our universe, transactions per second are becoming less important than transactions per watt. If you think about battery life on a phone or a tablet, I bet you all have an app that you will not run when your battery is kind of low, right? Or if you're going on a long trip and you're not going to be able to recharge for another 6 hours, you're like, no, that's not the game I want to play right now. That game really chews up my battery. You don't want to be the application that chews up the battery, whether it's on a phone or a tablet or anything else that needs to run on battery life. Or let's go the other end of the size extreme and think about a data center. I read that 90% of the cost of a data center, one way or another, is the cost of electricity. And when you reduce the electricity that the machines are using, you reduce the cooling load. Most of them have to be heavily cooled. And you can have an incredible impact, and that's real dollars, on either having less machines in that data center or running that electricity bill so much lower. So if you could cut your transactions per watt so that you got 4 times as many transactions or 50 times as many transactions per watt, think what you'd be doing to that data center costs. Now, there are some downsides to the GPU of what it can and can't do, but these differences have added up in the past to being that the CPU was for mainstream programmers, that everybody could do it, and the GPU was for sort of wizards or gurus or experts who went and learned how they worked, why they worked, and how to make them work well. And one of the goals of C++ AMP is to take that GPU programming to the mainstream so that you don't need to know all of this and you can still write code that will be faster or lower powered, if that's what you want. So it's mostly a library, and it's a library that comes with Visual C++ 2012, which, as you know, is in beta now. My demos today, I'm using the version that was released to the public on May 31st, and you're welcome to download that same version and play along and follow along. You don't need to set any project properties or create any special kind of property. All you do is you include amp.h. If you've used the PPL, you know you include ppl.h, right? And the contents of that header file are mostly in the namespace concurrency. Now notice that's a concurrency with a lowercase c. The PPL was in concurrency with a capital C, and it's moved down to lowercase, and C++ AMP is in concurrency with a lowercase c. There's an alias for now, so it doesn't matter, but you might as well do it the new way. And in that library, there are some things I'm going to drill into more on the slides that follow. There are some classes to represent data on the accelerator, array and array view. There's the concepts that you need in order to describe the size and shape of that data. That's an extent or a position within that data, that's an index. And there's a representation of an accelerator so that you can, for example, ask about its capabilities and its properties. And an accelerator view, which lets you specify some things about the way that you use that accelerator and give data back and forth to it. We'll go into all of those classes when the time is sort of appropriate. Then there's a function, actually several overloads of a function called parallel for each. Now, who's used the PPL? I got about a third of you, and you recognize parallel for each from there. This is yet another overload, or several, of parallel for each. And much like that one, it takes the range over which you want to do something parallelly and what it is you want to do. Simple as that. And then that what it is you want to do will get executed for each thread. But unlike a situation where you have 8 cores, this is massive parallelism, so it's going to be executed over thousands or more. The GPU is different than the CPU, as I mentioned, and there are some things you're not allowed to do. I'm going to drill more into that on a later slide. But when you're setting up your parallel for each and you're setting up your what to do needs to be marked with this new language keyword restrict. So this is an extension that is in the Visual C++ 2012, and anyone else who wants to implement it is going to have to include this language extension of this little keyword. And it's kind of like const. You know, if you say const int I equals 3, and then later you say I equals 4, you get a compiler error. So restrict at AMP says, I'm only going to do things that are okay to do on an AMP accelerator, and then if the compiler catches you doing something that you can't do on an AMP accelerator, you'll get a message and you'll be able to fix up your code. So if you start nowhere else, you start with parallel for each, because this is how you get your work done in a parallel way. That's why we call it the entry point. You pass in how many threads you want. I'd like a million threads to do this calculation. And there's a difference in the C++ AMP world between a million threads in one long line of a one-dimensional sort of vector, or a million threads in the form of 1,000 by 1,000 square. So you pass in not only the number, but also the shape of your calculation space. And then what it is that you want to do. And for us, for modern C++ developers, what we want to do is represented with a lambda. It's just, lambdas have changed everything in terms of using functions and algorithms instead of the built-in language fors. And although you can, in theory, write C++ AMP code using function pointers and function objects, I always use lambdas, and I suspect that you will too. And then you mark that lambda as being restrict at AMP, meaning I promise I'm only going to do things that are okay on the GPU. And the parallel for each deals with getting all that work and data onto the accelerator. The calculation will happen there. You don't wait for the calculation to complete on the accelerator. Okay? It's scheduled, off it goes, and your parallel for each falls through and control passes to whatever you have after that loop. Now, in my demos and in most of the samples that you're going to run, what we usually do immediately afterwards, the next line is something like printing out the answer. So we don't really get an opportunity to move on and use the CPU for something else. But in your real applications, what you might do on the next line is read another file or start some other sequential processing so you can have some significant activity on the CPU while your other calculations happening on the GPU. And that's a real benefit that will happen in real applications. The demo apps tend to, add up all the numbers and then tell you what the total was. So we may have to block and wait for the answer to come back, but that's not what would happen, the pattern in your apps. So I want to show you some code. You're not seeing double. Both halves are the same right now. And this is nice, simple code to add two arrays. And in this particular example, I'm using some like old school C-style arrays. So this function takes in just pointers, integer pointers. So you can guess from looking at this that PA is pointing to some array called A, PB to B, PSum to sum, and that all three of these are n elements long. All right, and C-style arrays don't know how long they are. You can't ask them like a vector. So we have to take in n as an argument. And then we're just going to sequentially loop through from I equals 0 to n. P sum at I is equal to P at I plus PB at I. Okay, that's easy to follow. And this is not much harder to follow. We're including amp.h and using namespace concurrency. And then we're declaring these three wrappers. Array view is a wrapper for data. In this particular case, the data that we're wrapping up is on the CPU, and it will be wrapped up so that it can be accessed also on the accelerator. Each of those array views, it's a template. We're saying it's an array view of integers, and it's one-dimensional. The first argument to the constructor is the size, which is n, and the second argument is the data that we want to wrap, which is PA. Now, array views can be, for example, square, and they can wrap up data that's kept in one long C-style array, and I've got a diagram showing you how that works in a little while. In this case, the array view is one long, one-dimensional, and so is the data that it's wrapping up. So A is an array view wrapped around PA, B is wrapped around PB, and sum is wrapped around pSum. The sequential for loop is then replaced with a parallel for each that has two arguments. The first argument is how many threads you want and the shape, and that's done in the form of an extent. An array view has an extent, a one-dimensional array. That extent is a one-dimensional extent. A two-dimensional array view has a two-dimensional extent, and so on. In this particular case, I could use the extent of A, or the extent of B, or the extent of sum. It doesn't matter because they're all the same. Or I could create a new extent out of nowhere built around the number that is in n. And all four of those approaches would work. It's sort of becoming a paradigm or an idiom. Most of the time we have a formula for the elements of the answer. So you're multiplying two matrices together. You know how to calculate each element of the result. So as a result, I very often see that the extents that are used are based on the answer we're trying to get. How many elements are in the answer? So for this particular case, you could also have used the extent of A or B, but it's kind of normal to use how many elements are in sum. So that's the first argument. The second argument is a lambda. Gosh, I love lambdas. I'm going to convert you all to being lambda lovers if I can. So this lambda captures the array views by value, and it's passed in an index, which is where you are inside that array view. And for each thread, we'll have a different index. Okay, so if we're adding up 1,000 elements, there are going to be 1,000 threads, and each one of them will represent a different point within that sum that we're calculating. Then it's marked as restrict amp. Then the body of the lambda in the braces is very much like the old body. We're still using square brackets. I mean, it's an operator overload. The square bracket on an array view is not exactly like the square bracket when you're talking to an integer pointer, but it sure looks the same, and it feels the same to you. So sum at I is equal to A at I plus B at I. Fine. And then after these loops have run, sum will have the answer in it. Okay? Because that array view is wrapped around that integer pointer, when we come out of there, pSum will actually contain the answer to our integer addition. So this is not a very big change from the code that you're writing today, and it's the sort of change that you need to make to get the sort of performance benefit that you saw in the Cartoonizer demo. So I just want to annotate those pieces again, and this is partly so that when you get the slides, you don't have to remember what I said or play the recording. So here's the array view wrapping up the data that's on the accelerator, the parallel for each that's going to execute that lambda once for each thread, the restricted amp to make sure that this is a legitimate GPU-friendly set of code inside my lambda, the extent, how many threads and in what shape, index, each thread will have a different value of that index, and then using the array views, the copying of the whatever PA points to, whatever PB points to, actually happens when the accelerator goes to use that data. So I don't have any code on there to say, now please copy PA into the array view. Don't need to do that. It does that for me. It also copies the answer back for me. So here's extent. You can have almost any number of dimensions you want. You're actually limited to 128. It's always dangerous to end a sentence with should be enough for everybody, but I do think 128 dimensions should be enough for anybody. And if that manages to come back to haunt me, so be it. I'm just going to show you 1, 2, and 3-dimensional examples because I actually think that's what we're mostly going to work with. So E is a 1-dimensional extent with 5 elements in it. Now they're row major. So F is a 2-dimensional extent, has 2 rows and 4 columns. And G is a 3-dimensional extent. It has 2 kind of sheets of these cubes, 4 rows and 3 columns. And we do indexes into the extents using exactly the same notations. So I is an index into the 0, 1, 2, 3 of that 1-dimensional extent. J in the 2-dimensional extent is in the 0, 1 row and the 0, 1, 2 column. And K is in the top sheet, so that's 0. It's in the 0, 1 row and the 0, 1, 2 column. I have these diagrams in the book, and most of the time when I was writing code and going through samples for the book, I would have these up in the background and be flipping over to them, counting over, yep, yeah, I'm definitely using the right dimensions. It's possible you have different dimensional schemes in your head. These are the ones that we use in C++ AMP. And this is important if, for example, you're writing something like Cartoonizer where you need to look at the neighboring pixels. It's important that you are actually defining neighboring the same way. So array view is great when you have a collection. Now I happen to show you a C-style array, but this works for standard library containers as well, which would be a better thing if you're writing your app from scratch. Use standard containers. If you're connecting to some code that's already written that has old school arrays, that's fine. It can also wrap data that's already on the accelerator. And that's sort of an advanced technique, but you should know that it can wrap things in both locations. And we say that it's dense in the least significant dimension, by which I mean if you think back to that extent and index diagrams, 2 elements that differ only in their least significant dimension will be next to each other in memory. It's kind of an implementation detail, but GPUs love working on memory locations that are all next to each other, nice neatly in a row. You have to say an array view of what? It's an array view of ints, or it's an array view of floats, or whatever. And you specify the dimension and the rank whenever you create one. And then you will have to give it an extent in the constructor. So if you did have a vector, this is a standard library vector of ints called v that's got 10 elements in it, and then you were to declare a 2-dimensional extent called e of 2 and 5, and then create yourself an array view called a using that extent and that vector. The diagram here is showing you how, and that we do this row major mapping, how the elements of v will end up being represented inside the array view a. You can do it all in one line. There's a couple of helper constructors available to you, so you could just pass in the dimensions when you were constructing the array view in the first place. And the nice thing about array view is you don't have to write any code to copy the data into the wrappered array view or out of it when you are done. So that's all taken care of for you just implicitly. Oh, you're talking to the array view on the accelerator? We better make sure that the data has been copied up here. If you were wrapping some CPU vector, it's been copied from the vector up into the array view. Oh, you're back on the CPU now talking to the vector. We better make sure that the answers have been copied back from the array view as where they were calculated on the accelerator. So time to show you some actual code. Cartoonizer is fun, but its code is a little much to ask you to read. So you'll be able to get it eventually from the book's website, but for now I'm going to show you something a little bit more readable. We're going to multiply matrices. I know it's very exciting. In fact, let's just review how we multiply matrices. I'm going to multiply A and B, giving the answer C. And the dimensions, the M, W, and N here, are exactly the same as what I have in my code. So the element C00, we're going to take the whole top row of A and the whole first column of B and pairwise multiply them. So A00 times B00, and then add that to A01 times B10, and so on. We're going to start with a sequential, and you can just see that the code is exactly that. We're going to go across the rows of C. So down the rows of C, across the columns of C, and for each element of C, we're going to make this temporary result object and loop through W being both the width of A and the height of B, figuring out our position, because A and B in this code are long, thin vectors, figuring out where exactly we need to be, multiply those elements together, keep a running total, and when, that was not a good plan, and when we've done all of that, store the result in this vref, which is these are all vectors of floats. Now before that loop runs, we initialize the array. It's simply calling out random numbers and sticking, these are floats, sticking random numbers into the arrays so that it's a little different every time I run it. The reason I'm storing this guy here in vref, and you probably think I want to store it in C, is that I'm actually going to compare the sequential results to the C++ AMP results to make sure they're correct. And especially when you're first playing around with applying C++ AMP to a calculation, there's a lot to be said for having the sequential way to do it, having the parallel way to do it, and making sure you still get the right answer, because correctness is a feature, and it doesn't matter how fast it is if it doesn't have to be right. If it doesn't have to be right, I can beat all your code. I'll just say 7. I win. I'm the fastest. Oh, you wanted the right answer. Well, okay, a little harder then. So we're going to stick the answer in vref, and later we'll compare C and ref. Now, a nice trick in this, which again probably won't be in your code, is that we actually, this is a lambda. So these loops are easy enough to read, 4, 4, 4, but they're actually all in a lambda, which is being passed to this time func. And the details of time func are out of scope for how long we have today, but it's doing a proper how much time passed, and it does all the right things to make sure that that's a fair comparisons of times. So we print out how long that took, and then we call time func again on a slightly longer, not very much, slightly longer lambda, and this is doing things the C++ AMP way. So I have 3 array views, very much like the 3 array views that were on the slide, for A, for B, and for C. And I have a couple of tiny little optimizations. I'm doing some hinting here by making A and B array views of const float. I'm hinting to the system that, hey, you know what, they're not going to change. That saves them from having to be copied back. It won't be changed on the accelerator. And I also throw away any data that's in C, which saves me from copying it up in the first place. These being vectors, they'll be 0 initialized, so they'll all have zeros in them. But why should I pay for all those zeros to be copied up there? I don't need them. Having done that, this is very much like the sequential code, except that I don't have the 2 for loops for each row of C and for each column of C. They're replaced with this square-shaped parallel for each. Well, not necessarily square, rectangular, right? A parallel for each over a 2-dimensional extent, which is the extent of C. This will give us 1 thread on the accelerator for every element in C. Up here, I have my sizings. So if this is quite large. This is, I think it's max int, 65 something. So a lot of threads. This code inside, same thing. We're going to go across the width of A, which is also the same as going down the columns of B. You could write that as mb.extent at 0 if you wanted. And create that partial sum and put it into result. When you've gone through all of the columns of A, then you put the result into this C. I told you that we didn't have to synchronize. We are synchronizing here to make sure that the time to copy the data back from the GPU is included in the timing. Otherwise, I'd be showing you overly optimistic timing results. Then we're just going to run through and make sure that VC and vref are the same. They surely should be. And if they did, I'll print out that it passed. So let me run this now. So the CPU time, the sequential time, and I've chosen a fairly small workload deliberately so that you can see a quick demo. It's interesting if you want to multiply all these numbers by 100, but then the talk would take a little longer. The CPU time, 65 milliseconds. The GPU time, 14. So it's not a 50 times speed up, but it's still pretty good. Right? We're dividing by 4 or 5, and I think most of us would be very happy. That's our overall time, too. With the cartoonizer, we were just focusing on the actual cartooning. Here we're looking at the slightly bigger part of the puzzle, including copying the data to and from the accelerator. So that code didn't look that different. Right? This is the sequential, 3 for loops, maybe not the world's most readable code. This is the parallel. We managed to actually have just one rectangular for loop and then the other one inside. You can read this. You can see what this does. And now it runs in a quarter or a fifth of the time. If you take nothing else away, you can take that away from this talk. There are ways to take even more control of performance to make it go even faster, but you can just walk up to it, use the parallel for each, and if you have a data parallel problem, get the performance boost. So multiplying matrices is a nice data parallel problem because we're doing exactly the same things to each element. We're not, oh, if it's odd, you have to do that, and if it's even, you have to do this other thing. No matter what it is, just multiply these together and add them up into a partial sum, and it's very happy to do that over and over again. I put the lambda as being restrict amp. I've mentioned a couple times there's only certain things that you can do on the GPU. It's really not a bad list. Many of these are things that you were not doing anyway. Occasionally, you may have to rethink your algorithm a little bit in order to make it GPU friendly. So first of all, just as you know, if a function is const, it can only call things that are const and so on. Once you say something is restricted amp, you're welcome to call another function, but that function has to be restricted amp. Also, it has to be visible to the compiler that it is, which tends to mean that it has to be in line. Only certain types are allowed, and specifically, a char is not allowed. So int and unsigned int, float and double, they're all fine. A char is not so fine. You can make structs and arrays of those types, so you can build up what you need. And when you start to get really heavily into performance, you can argue about structs of arrays versus arrays of structs, and they each have their place. You really aren't going to be doing pointer manipulation. Okay? You can't have double indirection, for example. You can't have function pointers and recursion and things like that. What you saw with the matrices, nice, simple, an array of floats, do something, multiply 2 floats together, add them up, that's great. Something more complicated involving multiple indirection, virtual functions, function pointers, that's not GPU friendly. Here's the sort of fine print list that you're welcome to go through, but I'm thinking that many of these are things you really weren't using. The only one you're really probably going to notice is exceptions. You can't have try or catch, you can't throw exceptions. So if that's something that you need to be aware of, you sort of need to have that restriction in mind. Other than that, I think you won't mind this stuff. I had a question. Will you get a compiler error? Yes. When you do a restrict amp, even something as simple as saying, char I equals 0, you'll be told you can't do that. It's not compatible. Yeah. If you forget the restrict amp, then the parallel for each will get you an error. Yes. ArrayView is easy and fun to use because it wraps up existing data wherever that data happens to be located, and because it does the synchronization for you automatically. But sometimes people don't want a wrapper, they want a container. And for that purpose, C++ AMP has an array. So it's a multi-dimensional array. It has an extent. It's an array of whatevers, of ints or floats or whatnot. It's type safe. And the storage lives just on an accelerator. So then you can put data into this array if you want, for example, by copying from a standard container. And you can take data back out of it by copying perhaps into a standard container. Generally, your lambdas that you pass to parallel for each should capture everything by value. And you'll get errors if you try to capture certain types by reference. The one type that you will always capture by reference is an array. So if you have any array views, you capture them by value. An array, you capture by reference. And that's just, the compiler will tell you if you get it wrong, but I'm just telling you now so that you don't get frustrated. You explicitly copy the data in and out. Other than that, it's pretty much an identical sort of API to ArrayView. So here in the sample code on the side, we're making a vector of ints and an extent, a two-dimensional extent that's 8 by 12, setting up an accelerator in some way that is out of scope for the slide, and then declaring an array, a two-dimensional array of integers with that extent on that accelerator, and then explicitly copying the data from v.begin to v.end into A. And notice the direction on these copies. This is C++ AMP, not C AMP or C with classes AMP, right? So just as in the standard library, we say from, comma, to, that is also what happens in C++ AMP. So we're copying from V to A. And we're happening to use the copy async so that we'll fall through and keep doing stuff, and that copy will go on meanwhile. Then we have a parallel for each that captures that accelerator by reference, and all we're doing is adding 1 to every element. And when we're done, we explicitly copy A back into V. Is that how I would do it? No, I'd make an array view wrapped around V. But any code that actually, went off and calculated the individual elements of A or whatever else I needed to do wouldn't fit on the PowerPoint, right? So it feels just like an array view most of the time, except it doesn't copy for you automatically. Now, some of you may have noticed when I ran the array multiplier that there was another piece of output referring to a tiling. If you want to take more control over the way your calculation is done, for some problems you can get a significant performance boost using something called tiling. You don't need to understand tiling in order to use C++ AMP, but if you understand and use tiling, you can get the absolute most out of C++ AMP. The point about tiling is not so much that your calculation is done in pieces, because that kind of happens behind the scenes for you anyway. The point about tiling is that it enables access to a small programmable cache. Your CPU has a very large cache. In fact, it has a series of different caches that are managed for you automatically. But in the GPU, the cache is quite small, and the programmer is in charge of it. Now, it's a good cache. You get to the memory, so the GPU has this chunk of memory, the CPU has this chunk of memory. We've been copying things back and forth from the CPU's memory to the GPU's memory. But there's this cache that's 100 times the speed of accessing the global memory on the GPU. So if you think again about multiplying matrices, and think about that first row of A, we use that first row, each element, to calculate C00. We would also use each of those elements to calculate C01 and C02 and so on as we go across the top row of C. And every element in the second row of A would be used for the second row of C. And similarly, the elements in the various columns of B are all used multiple times. So if we could put that data into the cache on the GPU, then our calculations on the GPU would go a ton faster. But the problem is, it's not that big a cache. So if you have 1 million data points in A and 1 million data points in B, you can't just stick all 2 million of those into the GPU cache and there you go, because it's not going to fit. So what tiling does is breaks your extent up into tiles, and each of the threads within a tile, they all share the same cache. Then in a different tile, they all share a different cache. And then you change your algorithm a little bit so that you copy things into the cache and then use them repeatedly within that tile, and then a different tile works with its own different copy. So if you only use each individual piece of data once, like in our array addition, you probably wouldn't gain a lot of benefit by gaining access to this cache. But if you're going to use each piece over and over again, you will. However, it gets a little more complicated to try to do the work. A typical pattern. I'm going to make a thread of, 256 threads in this tile, and they're all going to share this cache. And we'll copy 256 pieces of data from A into the cache and another 256 pieces of data from B into the cache, and then we'll set to work using those repeatedly to calculate our little share of C. But these threads are parallel. And the whole deal with things being parallel is they don't happen in order and they don't wait for each other. So imagine that I'm some thread, representing some index about 100 out of the 256. And I've done my bit. I've copied my data into A and B, and I'm ready to start using the cache to calculate C. Well, I can't just start using the cache because maybe the other threads have not yet finished putting their data into the cache. And these race conditions will give you correctness bugs. So you have to use the barrier that's on the tile to wait. So life gets a little more difficult. You sort of say, I'm going to copy my stuff into the cache, and then we're all going to wait here. And when we all get here to the barrier together, then we can all go over the barrier together. And now I can start using the cache, and I know that everybody else has done their bit, and we got past that possibility. So this makes your life a little more complicated, but it can create some very dramatic speed-ups. The demo that I showed you didn't even particularly go faster when it was tiled, but in the book we do a number of things where we see minimum of 50% speed up and sometimes substantially better than that. It's problem specific. A lot of it has to do with how often you use each piece of data. But rather than spend the rest of our time on something difficult that you don't need to use to get started, namely tiling, I wanted to really show off to you what's happening in Visual Studio. Because the debugging and visualizer support for C++ AMP is probably one of the reasons you would choose this way of speeding up your code. You're going to use a tool you know. Of course you get like IntelliSense and you know, semantic coloring and easy integration with TFS and all that kind of stuff because you're using C++ and you're using Visual Studio. But specifically around the parallel code, there's this support for the debugging that will give you that rich experience that you should be hoping for. One minor thing, and it's not a big thing, when you're doing a run, you're either going to hit GPU breakpoints or CPU breakpoints. Who's got their Visual Studio on C++ settings? Wow, like a quarter. I would have thought it would have been more. And this side of the room far more than that side of the room. Did you guys like pre-sort yourselves? That's kind of weird. If you're on C++ settings, you actually have a drop-down right next to the debug button to choose whether you want to do GPU only or native. Auto and native only are going to be the same in this choice. If you're not, then if you're on C# settings or whatnot, just go into your properties for the project and you can choose debugger type. The other minor detail is that today you're going to debug on Windows 8. You can't debug on Windows 7 today. I am not privy to when that will change. Don't ask me. So you're debugging. Fine. You know how to debug. You set breakpoints. You hit breakpoints, right? Then you come down and look in the autos window and look at the values of things, and they're red if they changed recently. You look at the call stack. It's not a very exciting call stack because for main I called into a lambda, so it's not exactly a fount of information in this screenshot. But, you know, for everything that call stacks could ever be for, there it is. And you can hover over things. So in this screenshot, I hovered over result, and you can see its numerical value. You can see the little pin there waiting to be pinned. I could pin that data tip. This has nothing to do with being parallel. This is just debugging in Visual Studio, right? This is what we expect. So it would be awful if I told you that this stuff went away, but it's just kind of ordinary that it's still there. It was actually a lot of work for somebody, probably more than one somebody's, but for us, we're just like, yep, that's debugging for you. Now they added some more capabilities because you sometimes need to know different things in order to successfully debug some parallel code. So in this screenshot, this is actually the code, if you care, is the tiled code for matrix multiplication. And there's quite a lot of action going on in this screenshot. First of all, the slide purports to be about GPU threads, and that's what you see down in the bottom where the locals were before. And this is showing you different threads being in different places. So 252 threads are at line 130, which is a tile barrier, and 4 threads have gone past that tile barrier. They're the first guys to get to go, and they're moving on to do the calculation. In this case, they're using the cached data. By the way, at the top of this screenshot, you see it says tile static float. That's the second keyword that C++ AMP added in the extensions. This is a tiny, tiny change. It represents another storage specifier, and specifically that's that GPU programmable cache. In the margin, you can see the red dot. That's my breakpoint. You can see some wiggly lines, and then you can see some more wiggly lines with a yellow arrow on top of them. So those are thread markers, the wiggly lines, and they indicate that some threads are here. And one of them, the yellow arrow happens to be at. That's what, if I hover over things, that's whose values I'm going to see. or what the locals window would be showing me, whose values I'm going to see. And not surprisingly, the wiggly lines correspond to what's happening down in the GPU threads window. There's a number of different ways to give you what you want to know. The parallel watch window, I pulled this up to be next to the code so that I could get more verticality out of it. It's just like a watch, and you can right-click a variable and choose Add Parallel Watch, or you can go in here and type things. And I'm looking at the same variable, in this case sum, across a number of different threads at once. Because this is a tiled algorithm, every thread has both a tile index and a thread index. That's why you see several pairs of indices going on. So I can see in the GPU threads at the bottom here that I have 4 threads blocked, and I have 4 threads active, and another, what is that? I took my glasses off. 248 threads blocked and waiting at the tile barrier on line 130. But I can see in the parallel watch window how sum has just changed for 4 of those threads. And it's exactly the same things that you're used to. Red for something that's just changed, black for something that was the same last time you stepped over. And all those habits and reflexes that you have around debugging are fully going to still work for you in this universe. There's more. There's the parallel stacks window, which you may have used with PPL. It's very cool also for C++ AMP work. There's a whole pile of functionality that let these windows work together. So I could go into the GPU threads and flag a group of threads that were, say, at the barrier, and then go into the parallel watch and filter to say, just show me the flagged ones. You can also filter like, just show me ones where sum is greater than 100, or where some other variable is 1 or 0, so that I can work out which threads I sort of need to pay attention to. You can even take over the scheduling and freeze and thaw threads, choose to run groups of threads together, entire tiles at once, that kind of thing. So it's a very powerful GPU-aware, parallelism-aware debugger. And the concurrency visualizer, which if you've used PPL you may have met, is also now GPU-aware. And I'm actually going to switch over. This is kind of like when they take the lasagna out of the kitchen, out of the oven, you know, that they put in 2 hours ago. This is a concurrency visualizer trace that I ran for the cartoonizer, doing essentially the same demo that I just did for you to open this session. The first long, low green splodge here, that's I did this in Canada, so this is 6 seconds. Because I got to move to Europe for performance reasons. That's the 6 seconds of cartoonizing the single picture with a single core. And then this lump right here, that's the 1.5 seconds of cartoonizing with all 4 of my cores. And then this, and I'm going to zoom, but it doesn't really help. Does anybody see that tiny little? That's the GPU activity of doing that same cartoonizing on the GPU. It's a little hard to spot. Here, I took the picture and I did it up to like 20. And then I finally managed to see a little bit of the GPU activity. And this takes about 2 minutes to do with a single core. So you very clearly can see the speed benefits. Now, Cartoonizer happens to have timing code built in and numbers in the corner. Let's say this took 6 seconds, this took 4 seconds, this took 1.2, whatever. You're probably not going to build that code into your apps. So how are you going to know if you're getting anywhere, if you're gaining anything when you decide to parallelize your code? The answer is the concurrency visualizer. If you do a run in which you do things 3 different ways and then you see long, low stripe, shorter, higher stripe, almost unnoticeable stripe, and tiny little peak of activity down here, you're like, oh, I think I gained a benefit, right? I can't be 100% sure, but I think my app was quicker. Now, the nice thing about Cartoonizer is that you can see as soon as I click the button that the cartoon comes back and you know you gained. But depending on the calculation that you're running, it may be harder. Or you may be going to a lot of trouble to write an application that turns out to be sequential. You know, we see that where people will have some contentions or race conditions, and then they have synchronization so as not to have collisions. And then basically everyone's lining up, and you've accidentally written a sequential application. And the concurrency visualizer can really bring that home to you, and let you see whether you've actually gained anything from what you're doing, and be able to answer some questions about the improvement that you may have created in your application. So I repeated these screenshots in the deck just because it's usually easier to get you the deck. And I don't know if you can see the tiny little green splodge there, and that's a close-up of the little green splodges. You know, let's just go back to this for a minute. One of the things that you have to think about when you think about speeding up your app is that it's not always about speeding up your app. So it's cool for Cartoonizer to take something from multiple seconds to 50 or 100 milliseconds, and that might be what you would use it for. But you might instead decide that you just wanted to do more calculations or to work on larger data points. So don't just think about it as a way to get faster. Think about it perhaps as a way to get more accurate or more complete results. I have a number of circumstances where really you're constrained by a certain amount of real time to do your calculation. The example I like to give is, say you have a stock market model, and it looks for maybe holes or gaps or problems in the stock market, and it will tell you what to do. And it's a wonderful piece of code, but it takes 30 days to run. Okay? So you start running it today, and then late, almost at the end of July, it tells you what you should have done today. And it's kind of a little late for you to be able to react, right? So you might have in the past said, I'll have to settle for being less accurate so that I can get my answers in a reasonable window. But if you could speed that up, and probably it's very data parallel, you're doing the same comparisons across a huge quantity of data. So if you could speed that up by 100 times, instead of 30 days, it would take a third of a day, which is 8 hours, which is just overnight while the markets are closed, right? So you could start it going at the end of the day, and in the morning it would tell you what to do, and you could do it. And if you do that, can I please have a commission on whatever you make? The other scary one I like to talk about when it comes to speeding up your calculations is passwords. Probably you have a policy of having to change your password every 90 days, maybe every 30, depending on where you work. And you know what? If it takes 90 days for someone to crack your password by brute force, and you change your password every 30 days, you feel pretty smug. I'm okay. I'm not those people whose LinkedIn password was LinkedIn. Don't put your hand up if you were one of those people. But here's the thing. That's pretty darn data parallel too, right? Brute force password cracking. It's doing the same operations over and over again, and they're pretty simple. So if we could take that from 90 days to 1 day, now how safe does your password feel? Right? So for some things, it is about speeding it up. For others, it's going to be about, I can now use 1,000,000 data points instead of 1,000 data points and still get my answer before the market's open, or still get my answer medical imaging, detecting anomalies on X-rays, MRIs, CAT scans, PET scans, blah, blah, or facial recognition software. They are always saying they're going to have software in the airports to spot the bad guys walking through. It's just like the stock market. It's not helpful to say, yeah, 3 weeks ago there was totally a bad guy here in the airport. We're sure it was him, or her, I suppose. So there's cases where you want to get a time window and put more and more and more accuracy into that time window. You don't want to tell people they have a tumor if they don't, or vice versa, and you don't want to know that everybody is a bad guy because you're being me and saying, 7. I can get you an answer really quickly, so you want an accurate answer within the time you have available. And that's a case, again, where the concurrency visualizer could help you to ensure, I've got this much time available, how much of it am I using? Okay, let's put a few more passes in, or let's put a few more data points in and see if we can still stay in our same time window. So when people are going to ask you, what is C++ AMP? Yes, you can tell them it stands for Accelerated Massive Parallelism. But the real answer is what it will do for you, how it will speed up your applications, or how it will enable you to get better answers. So first and foremost, C++ AMP is C++. It's the language you know in the tool you know with the productivity that you've developed over however long you've been using Visual Studio. You recognize the syntax coloring. You know the keystrokes to make certain things happen. You're still going to be doing those same things. It's mostly a library. That means you can use it to build MFC apps. Cartoonizer is an MFC app. You can use it to build a console app, by which I mean like, main at argc, argv, that kind of console, DOS prompt. So my matrix multiplier and many of the samples that they'll show you will be those kind of console apps. But it can also be Metro app. So I'm working on a Metro app that manipulates pictures as a photo viewer. And one of the things we want to do is add cartoonizing into that. So you're flipping through your photo album and you want to make a cartoon out of one of them, and that leverages C++ AMP. So you're not restricted to just certain kinds of applications because it's a library and you can use libraries from pretty much anything, right? You've got this great support in Visual Studio, and at least in theory there will be support from other compilers for other platforms so that you have that portability. But of course the other important portability that you have right now is that hardware portability of it doesn't matter who makes the video card, you're not restricted. Most of us, I don't think, know who makes the video cards in the machines that our end users are using. And we don't want to have to know in order to gain this performance boost. I have some references here. I know it looks like I'm cheating, like, hey, she made her book really big and the rest are really little. But that's because pretty much all the rest of them are, in fact, the only URL you need is the giant one at the bottom, blogs.msdn.com/native concurrency, which is right here. This is the blog of the parallel programming in native code. So it's AMP and PPL together. And you'll see right over here in giant letters it says start here. This is very subtle. Okay? This is the stuff you need, this whole column of good stuff. So there's a link to the forums, to the samples. There is a link right here to my book and to that course. I want to show you the samples. There are dozens of them, and they tackle a wide variety of different things. You can download them, run them, read them, learn from them. The n-body simulation, that was used when they first announced it. You may have seen this with the planets kind of swirling around, and you keep adding more and more, and they slow down, and then you switch up to a different, let's use PPL, then they go a little faster. Okay, let's try using AMP, they go faster and faster. Let's use tiling, they go still faster. It's a nice dramatic graphical example. But both Cartoonizer and n-body, they're visual, so we can demo them. But you may be actually more interested in things that aren't about drawing pictures on the screen. They're about calculating some numbers. So there's a ton of other examples here that you can go through. So we have matrix multiplication, matrix transposing, histograms, that kind of thing. I kind of like these ones. These are the interop ones. People do ask me all the time, how can I use C++ AMP from C#? They're like, that's really cool. I love that technology, but I'm a C# developer now. How can I use that? P-invoke to a C++ project in which someone's using C++ AMP. That's how you use C++ AMP from C#. Okay, and that's what these two examples are showing you. So they're both a Windows 8 Metro style and a more traditional application that are written in C# and that are p-invoking over to a C++ library that actually is doing the calculations using C++ AMP. There's a whole sample related to measuring performance if you'd like to do it yourself, as well as some more complicated and trickier things. This link here is to my book page that I'm doing with Aid Miller, and there's a place here where you can sign up and actually look at the chapters while they're being written, because the publisher's been nice enough to put them there. And if you have experience with CUDA or HLSL or OpenCL or other kinds of graphics card based acceleration, they've written some fairly long and detailed white papers for people who know those words and know those concepts to help you map into the C++ AMP world. So take a look there also. And finally, there's even a deck that you can use if you want to go back to your employees and your colleagues and say, we all have to get on this right away. Daniel has uploaded some slides to help you to go through a presentation of your own. So really everything you need is on this link, and that's why it's the one that I put on the slides in giant letters across the back. And they blog, there's a bunch of them. And between them, somebody blogs almost every day, and it's super hard to keep up with. I mean, it's my job to keep up with it, and there's more and more, and they drill down into more trickier details all of the time. So you can start simple, and then when you try to get to something a little subtler, like here's a blog from a week ago saying, hey, what about a machine that has a graphics card, video card, but doesn't have a monitor on that card, and maybe doesn't have some of the configurations set up because it's a headless server. Can you imagine take a server and just like fill it full of video cards, like 10 of them, and throw a workload like this at it? Whoo! That would be great. And so there's a whole blog post about how to make that happen and what considerations you need to take into account to make that happen. So that's the URL you need, blogs.msdn.com/native concurrency. And here's what I want you to do. Who's already got Visual Studio 2012? Like 3/4 of you. So the other quarter, no more excuses. Go get it. Put it on something. Put it on Windows 8 if you don't have anything particular to put it on, so that you can play around, for example, with making Metro apps this way. It's pretty sweet. Download some of the samples. There's over 30 of them, so I'm not going to tell you to download them all. Pick and choose, and then play around with them. Set some breakpoints. Play with them in the debugger. See how things look as you step groups of tiles through your breakpoints, groups of threads through your breakpoints. And then try writing one of your own. I mean, maybe something thrilling and exciting like adding matrices, or maybe a calculation that you're actually doing in your real life that you think has a chance of being data parallel, that you think has a chance of speeding up a little. You could do that as a console app, as a traditional Windows app, or as a Metro-style app for Windows 8, whatever works. And then the most important step, if you're going to start writing some of your own, measure, measure, measure. You can't just assume that it will be 50 times faster because my sample was 50 times faster. If you write it poorly, if you write the kind of code that makes the GPU unhappy, you might actually make it worse. Okay? So you need to measure and be sure that you really are helping. Now, people say, I want to try this, but I don't have necessarily the video card that I need. There is a small sample available on that team blog called Verify AMP Devices, which runs through all the accelerators on your system and tells you whether in fact they are C++ AMP compatible or not. And if your card does DirectX 11, it will be compatible. If you don't have a DirectX 11 card, and you don't have really a way to put a DirectX 11 card in your machine, and some of the cards that are available, they cost like $100, so don't assume that you have to go buy some super high-end complicated thing. But if it's not an option, say you're in a laptop or whatever, when you're on Windows 8, there's an emulator called Warp, which will basically build a graphics card emulation for you out of vectorization and SSE. It won't be as fast as a high-end card by any means, but it will let your code run. If you have a strong belief that a lot of your target market might not have an accelerator of any kind in their machines, you can test, you can write code at runtime that tests to see what accelerators you have and only tries to use them if you have them. Now, what are you going to do if you don't? You tell me, it's your app. Like, you're going to put up a window that says, I'm sorry, you don't have the right hardware, or you're going to do the calculation a slower way, or do less passes, right? You're going to make that decision for yourself. But it's all available to you in code to be able to say, is there an accelerator? Is it an emulator? Does it have a monitor on it? And a few other bits and pieces of sort of properties of those accelerators. But it is important that, that you measure, because that's the only way that you're going to see the benefit that you're getting. There are some huge speed-ups available. I mean, people get excited about 20% faster. People get excited about 50% faster. So 50 times is amazing. And then if it turns out that in your app, oh, geez, I'm only getting 5 times faster, like, slap yourself. 5 times is faster, right? That's a good thing. I hope you get 50 and 100, but it depends how data parallel you are, and depends how much of your application is in that parallel part. If you have to read a file, that's sequential, right? If you have to write out the answer to a file, that's sequential. And if those two things take 100-somethings each, I don't care, hours, minutes, days, and the bit in between has been taking 1,000 and you can get it down to 10, that's great. But overall, you've gone from taking 1,200 to taking 210. That's only a 6 times speed up, right? Because you can't get away from the sequential part of the reading and writing. It's called Amdahl's law. And it's kind of unfair in a way. It says that the sequential parts will eventually come to dominate your execution time no matter what you do to the parallel parts. However, depending on how big your parallel parts are, if you have 100 something followed by 1,000,000 followed by 100, you're going to be super happy if you can get that million down to 10,000, right? And you will see that big overall speed up in that particular case. So here's the resources from the TechEd people. Those are not bad places to start in addition to the native concurrency blog that I told you about. And super important to me, please, please, please do your evaluations. In North America, I had 90 people in the room and only 13 evaluations. I know you guys can do better than that. I say the same thing every year. I love coming to speak at TechEd, especially TechEd Europe. And the way they decide who comes back is by evaluations. I love that there are C++ sessions in Europe. The way they decide what topics get sessions is by evaluations. So this is all really simple, right? You can do this. So I have, I believe, 5 minutes for questions. And thank you very much all for coming. Question here. Is it possible to have the GPU being used by more than one process? Yes, absolutely. I mean, normally speaking, your GPU is busy showing your screen, right? So if you had two services running and they're both trying to use AMP, I suspect there's more details on this in that headless server blog post from a week ago, but there's no reason why not. It's just obviously you wouldn't get the full power, but I don't think you'd be told too bad someone else is using it. Right? Tiling wouldn't really affect that. No. Question here.
What happens if you run an AMP-powered loop on a computer where the GPU doesn't support that? Does it throw an exception or just...
The question is, what happens if you try to run a parallel for each on something that doesn't have the right accelerator? If you didn't check to see if you had one and you just marched out and tried to talk to one, yes, you'd get an exception. Depending on what you're doing, when you set up the array views, they're put on the so-called default accelerator. And if you don't have a default accelerator, that's when you're going to run into problems. If you saw the code that set up an array that actually said accelerator ACC equals, that's the line that would have had a problem. So it depends on exactly what your code looks like, but you would get a runtime problem. And it would be nice for you to test first. You can get all the available accelerators and then iterate through that, see how many there are and that kind of thing to prevent people from seeing that. Sure. Question here. Can you choose a specific accelerator? Absolutely. We have a whole chapter in the book on mixing and matching, choosing the best accelerator, sharing the workload between multiple accelerators, and so on. It's obviously an advanced topic, but you can do it. Yep. Here. Can you change the tile size dynamically? Yes and no. Not technically, it must be known at compile time, be a compile time constant. However, we have more than one sample in which we use templates to get around that. So we templatize over the tile size so you can choose it at runtime. And it's true because your optimal tile size can be hardware dependent, can be different, not just even by manufacturer, but even on different cards from the same manufacturer. So it's a technique you may want to lift from the sample code, for sure. Back over here. Yes, in a virtualized environment, for example, my machine is boot to VHD, and it's perfectly fine. But for like VMs or what if I'm remoted in or all those details, you go to that same headless server blog post, the gory details are there. But it's nice that it works over a remote desktop because you might not have expected it to, and it does. One more here.
You mentioned the interrupt scenario.
Yes.
From C# to C++.
Interrupt from C# to C++. Mm-hmm.
In Windows 8 scenario, you still do the invoke, but use WinRT component.
Sure, you could use WinRT component. There's more than one way to skin a cat. Absolutely, and that's why there's two different interop samples on the blog. One specifically for the Metro style, and you also have to deal with data types when you're doing with that. So something that's say a bitmap image, what C# describes a bitmap and how C++ describes a bitmap or how WinRT describes a bitmap. There's lots of data types to go around, and maybe you need to do some conversion and marshalling and so forth. So lots of ways to tackle it. What's important, in my opinion, is to copy the minimum amount of data that you possibly can between the sort of universes. Yeah. Question here?
It's only available in Visual Studio 2012?
Visual Studio 2012, all the SKUs, doesn't matter, like you don't have to go buy Ultimate or anything, it's just part of what we have now. 2010 as your regular operation. So get yourself 2012 while it's, for beta testing, and test it. And if C++ AMP is compelling enough for you, then when someone says, why should we upgrade, you'll have an answer for them. All right. That is my time. I'm welcome to take more questions one-on-one. Thank you all for staying right to the end of TechEd. There's one more session. Be nice to those speakers and go to them too if you can. And I hope to see you all again next year.